Welcome to today's lecture in information security. Let me just check whether I have everything set up here correctly. Better. Okay, and then I will also open the slides here so that I can see something. And I will also follow the chat, of course, and the Menti. One more adaptation. There's always some tricks here that I have to do to get the light correctly. Maybe I can. Oh yeah, that's a bit better. Okay, so let's start. We talk about memory safety today, system security. That's what we continue with, and that's a topic that I prefer much over cryptography. But cryptography always, also is great. But it's just not my topic. My topic is system security, so that is what I want to talk to you about. System security. Memory safety is the first word that we want to look up, and I just looked it up on Wikipedia, and look what I found there. A definition: memory safety is a concern in software development. Okay. I also need to adapt this a bit. Okay. In software development, okay, so what does that mean for us? We have to go through that definition word by word. Concern in software development that aims to avoid software bugs. Okay, so memory safety is about avoiding software bugs that cause security vulnerabilities. So we will talk about security vulnerabilities. And these memory safety bugs, they are about dealing with random access memory accesses. So with memory accesses. Okay. Maybe an example in the definition is such as buffer overflows or dangling pointers. So let's talk about these in more detail. We will do that in the next few lectures. But let me give you some more details first. So maybe we should talk about when is program execution memory safe and when it's not safe. If it's safe, the following things do not occur. Access errors like buffer overflows or buffer overreads. If you read beyond the end of a buffer, that would be an access error, and they don't exist in memory safe programs. Invalid pointers, maybe you are dereferencing the null pointer, that would be an access error. That's a memory safety bug. Or race conditions. Race conditions, we all love them. They are memory safety errors, access error. Use after free, also an access error. The class of access errors, they have in common that this memory access is invalid, either, for instance, because the buffer is not long enough to access it at this location, or because the pointer has not been initialized, or because maybe the pointer was initialized but not at this time because it's a race condition, or use after free, maybe the pointer was initialized but in the meantime has been freed and now you can't access it anymore. Uninitialized variables, another type of memory safety error. For instance, the null pointer. So in the invalid pointer, maybe let's distinguish those a bit more. The invalid pointer, maybe this is more about pointers that were never meant to be dereferenced. Maybe I initialized it to an invalid value, not the null value. The null pointer maybe is easier to detect. Invalid pointers, maybe it's also a pointer that belongs to a different object that was passed incorrectly. And now you have an invalid pointer. Or maybe it is a location that, due to some of these, for instance, the use after free, has become invalid. Uninitialized pointer access. Yes, of course. There could be some random value on the stack in a variable. If I create a pointer variable, it could be an uninitialized pointer value in there. And this could also lead to an uninitialized pointer access or also an invalid pointer access. Memory leaks are also memory safety errors. For instance, if you have a stack or a heap overflow, If you allocate more and more space on the stack, that's a problem. If you allocate more and more space on the heap, that's also a problem. And we need to avoid these to make our programs memory safe. Invalid free is also a problem if you free some memory location and then you want to free it again. That's of course a memory error, because malloc might not understand that you already freed this location, and under normal circumstances your program should crash then. Unwanted aliasing. Yes, maybe you have different pointers, or maybe a pointer into some object, or maybe your environment casts automatically some pointer to another pointer. This can be problematic. Let's talk about memory safety violations also from a different perspective. In general, we distinguish two types of memory safety violations. And all of these previous examples fall into one of these two categories. Either it's a spatial violation, then the memory access is out of an object's bounds. See that I drag the colors a bit more here. A bit better. Okay. If it's out of bounds, for instance, we had this with the buffer overflow, the out of bounds reads, if you read beyond the end of a buffer, or if you have a null pointer dereference, for instance, also it's clearly not in the object's bounds if you access the null pointer dereference. So all of these relate to where does the memory access go. This memory access would never be valid, no matter when in the program's execution time we want to do that. It's never valid because it's out of bounds, it's an overflow, or it's not even initialized, it's a null pointer, for instance. The other type of memory safety violation is temporal violation. A temporal violation would be valid at one point in the execution time, but it's not valid at the current point in time. So it's a memory access that refers to an invalid object. It says use after free is one example. Accessing a pointer that you allocated with malloc is totally fine, right? But after you freed it, it would be use after free. But here you have to be careful. Use after free also exists with other allocation methods. For instance, you could use mmap and munmap and could also run into a use after free situation there. Or for instance, a local variable that you create, you pass the pointer to another thread, and then your function returns and the stack frame is removed, and then it's not valid anymore. And it's a use after free, because when you unroll the stack frame, it's freed automatically. A double free, also a temporal violation, because the free in general, freeing a malloc segment, would be totally fine, but freeing it twice is not fine. Use of uninitialized memory, if the memory would be initialized later on, it would be fine to access it. But you're accessing it too early, so that's a temporal violation. Temporal violation, it's just the wrong point in time where you try to access it. Okay, let's see. I have some questions already in the Menti, and I think it's a good idea to check out what they are. Okay, it's just about the music, so we can mark them as answered. So, just to give you some more motivation, why is all of this relevant? Why are we talking about all these memory safety violations? The thing is that they are really, really common. Memory safety violations, if you look at the plot here, that's the statistics from MITRE, about CVEs, and that's vulnerabilities by types. And if you take a look at memory corruption vulnerabilities, in the early 2000s, they were not too common because also the community didn't fully understand them at the time. And then they got more and more frequent. And this plot continued like that. We have more and more memory errors all the time. So this is the CVE database from MITRE. That's a US organization that tracks common vulnerabilities and exposures. That's what CVE stands for, common vulnerabilities and exposures. And that's just publicly known information on security vulnerabilities that we collect there. Okay. So let me continue with the next part. Many companies maintain two teams with the purpose to make sure that their systems are secure. And that's the red team and the blue team. The red team, the attackers that try to violate memory safety, and the defenders that try to ensure memory safety. So that's just for memory safety, but these teams also exist on a broader scale. So in general, you have an attacker team and a defender team, and they work separately. They also exchange with each other, but most of the time they work separately. Yes, and then of course they can play this as a security war game where one tries to break things and the other tries to prevent that. And there are capture the flag games where you can also play that and practice that. I see that for some reason the chat has gone missing. Is that correct? Let me just check where the chat has gone. Ah, yeah, no, the chat is there again. Okay. I just didn't see it for a second. But now it should be visible again. Okay, if you have any questions at any point in time, you can ask them, of course, in the Menti, but also in the YouTube chat. I also have the YouTube chat right in front of me. So there's a question. Doesn't Rust make all of these vulnerabilities obsolete? No, of course not. Rust makes some vulnerabilities obsolete, but we have memory-safe languages already since 30 years, right? Even more than that, 40 years. Why aren't these memory safety vulnerabilities all obsolete already? So if it's just a matter of the language, then I would say we shouldn't have had any memory safety vulnerabilities anymore since at least the 80s. But we are still here. We still have them. And the reason is that some code just interacts with the hardware, interacts with external other computers. And if that's the situation, then you will still have memory safety errors. Is there a tendency in which programs memory errors occur? My guess would be programs written in C. Yes. So in Rust, you would probably have fewer memory errors. It's not impossible. So in Rust, sometimes you have to use this unsafe keyword, and then in that range, memory safety errors can arise. But in C, yes, in C you have full control over everything that happens, so you also have to make sure that nothing bad happens. Red team versus blue team. Attackers and defenders play this game, and yes, the red team wants to try to find security problems, mount attacks, and if they do so, they have a success because they found the vulnerability before the real attackers that want to attack the company were able to find the security problem and mount the attack. The blue team, on the other side, tries to protect software and defend against attack. So in companies, red team and blue team are not criminals, but in general, these terms, you could use them also in a broader sense to always say, well, these are the attackers They could be criminals, but in companies, the red team work is essential for the blue team. What does the blue team defend against? If you specialize into information security, you will also maybe focus more on exploiting vulnerabilities or maybe on mitigating vulnerabilities. And there's a lot of depth into either of these paths. And you will not gain all the expertise on the other path if you choose one. So it is important to have people focusing more on that side and people focusing more on that side to really make sure that you cover all the things that you want to find. The blue team develops defenses based on what the red team found, and then the red team tries to break it again. And with that, you sort of play this game of increasing security gradually, step by step, making your systems more and more secure software, better defenses. And the ultimate goal would be memory-safe programs that don't have any bugs. So let's talk about the red team, or let's talk about attacks. What is an exploit? An exploit, there are different definitions, and I want to go through these definitions with you. And today in the lecture, we will also cover some theory parts on the theory behind exploits and exploitation. So what is an exploit? Different definitions from dictionaries, from Wikipedia, from Kaspersky. So let's go through them. A software tool designed to take advantage of a flaw in a computer system. Okay, so software that takes advantage of a flaw. Cause unintended or unanticipated behavior to occur on computer software. Okay, so you try to trigger something that no one has thought of. Okay. And then Kaspersky writes, if Achilles' heel was his vulnerability in the Iliad, then Paris's poison-tipped arrow was the exploit. Just as an historic reference here. But also what you notice here is software tool, unintended, unanticipated behavior on software. Something with the Greeks? I don't know. So what could it be? It's quite fuzzy. So let's maybe talk about what programs normally do, and then we can talk about what they do if they are exploited. And many of these ideas are from Hira Flake Thomas Dulien, who gave a talk at TU Graz a few years ago. He introduced a notion for exploits that is more heavy on theory, and that allows you to think about exploits also in a more formal way. What is a normal program? A normal program, well, a program, the machine computes something, right? And the program implements an algorithm that allows the machine to solve some problem, something to compute. Maybe it has to sort something, this program that sorts data, sure. Ideally, these programs are finite state machines. You might have seen them already in some other classes, that you can draw a finite state graph of a simple program that will be fine. We don't build machines that are exactly this, right? Our modern processors are not just, well, they are not finite state machines computing exactly that program, that solving exactly that problem. So what do we do instead? We build general purpose hardware, and this general purpose hardware is able to emulate these finite state machines. And programs basically emulate these finite state machines and act as if that's what your computer is able to do. So let's think about that. A finite state machine, we have transitions, we have states in there, and maybe here in this case we have example with the door is either opened or closed. And then in this graph, we can close the door, then it's closed. We can open the door, then it's opened. So we have the states here. Let me show them like this maybe. This is a state, this is a state. Then we have the actions in each state are open door, closed door, and then the transition is here, open or close. And there's also some transition condition that we don't have here. So this transition could have some additional condition here. Okay. States and transitions. So the input to our program will now just be processed by this finite state graph. If the input is closed door, we will move on to this next state. If the input then is open door or closed door, then we will move on to the next state. Okay. The finite state machine solves the basic problem of whatever you define, like sorting an array, or even something more complex in software. Everything can be expressed, or almost everything can be expressed as a finite state machine, at least on some abstraction level. There are many different ways to implement finite state machines. A simple password manager, for instance, could be this. You read a PIN. If it's correct, then you show the password list. And if it's not correct, then you show an error message and go back to the reading function. So now our finite state machine implements security aspects, right? We check, is this allowed? And then we would show something to the user. If our finite state machine is not implemented correctly, we could go into this state and show the password list, although we don't want to. And the security properties of our finite state machine, they are based on the inputs and outputs. If someone provides the correct PIN, then we show the password list. If someone doesn't, then we don't. So what we want from our finite state machine is that it should be practically infeasible for an attacker to get the password list if they don't know the input, the PIN. So we don't get the output we want if we don't know the input that is checked here. And let me just check the questions on Menti again, but also keep in mind that you can ask in the YouTube chat as well, and I will be able to see that right in front of me and don't have to check. Okay, let's see. Alice, okay. Okay, I'm not sure I can follow the story here. Let's just continue with the finite state machine and the CPU states. So if we think about an emulator for a finite state machine, a program that we write, the CPU has a lot more states than our finite state machine. And every state of our finite state machine is now represented by one or more CPU states. So we have a mapping there from a few states in a finite state machine to many, many states in a really, really complex CPU. For instance, if you read the PIN, this requires a lot of CPU states. The keyboard interrupts reading the keys, storing the text in memory. That's a lot of states to handle. And not every CPU state is represented in the finite state machine. For instance, imagine if you get an interrupt, not just the keyboard interrupt, but maybe a disk interrupt that has nothing to do with your program, then this is not even part of the finite state machine. So what CPU states do we have? And here we want to build up a theory of what normal programs and exploits, how they are different. So the first state that we want to discuss is the sane state, the CPU state corresponding to a finite state machine. So that means that we are exactly on this finite state machine graph and everything is fine, right? And we are in a finite state machine state. Then the transitory state, that's the CPU state during a transition, because during these transitions we will also have a lot of CPU states because the CPU has a lot more states than the finite state machine. And the consequence of this transition here will be we go back to a sane state. That means the finite state machine state is equivalent to the CPU state, like we wait for input. And then Heirath-Laake also defined a third case, and that's a weird state. That's a state where the CPU state does not correspond to a finite state machine state. And in this next example, I want to go through a code example, the simple password manager that we've seen before as a finite state machine, now implemented in code. And it looks like this. So here we have a main function. The pin is read. We have a while loop. And this while loop, so pin correct, just initialized to 0, right? Pin is read in a loop. We have the loop here, read pin. If the pin is pin times some number is some other value, okay, then it's correct. Otherwise, we continue here, okay. If it is correct, then we show the passwords and break out of the loop, we stop. Otherwise, we say it was the wrong pin and return to the read pin method. Let's check what these methods do. We have the read pin method up here. The read pin method reads a 16-byte, or it has a 16-byte buffer. Then it uses getS to read into this buffer. Then it uses getEnv. Well, if it's for debugging, then we print the buffer, and then we use return a to I to return the number that the user has entered on the terminal. The show passwords function. Here we have a file pointer, character pointer, size t. And what do we do with that? We open the passwords file as a stream, file stream, and then we read one line from this stream into this character pointer. GetLine allocates memory for us. It implicitly calls malloc. The length is also passed on here as passed by reference, so that we know how long is this line. And then we can print this line, so this password, and we do that on and on and on, and then we free this pointer here. And then we close the stream, and then we are done with that part. So where are we right now? We are here in our while loop, and that means we are in a transitory state, because that's not a state of the finite state machine that we defined earlier. So let's see where we go. We read the pin. This is still a transitory state. And now in the next part, we print this prompt enter pin, and that's actually a state that we had in our finite state machine. CPU state is sane. The state of the finite state machine is read pin. Okay, next step. Still fine. We are trying to read here, so that's still represented in the graph. This part actually should not be in there, right? It was not in our graph, but let's say we adapted the graph a bit. So this is still sane execution here. Then we have our A to I function here. This is again transitory. So now we are moving on to some other state. And then we go into the state, is it correct? So that's this line here. We set correct to 1 if it was correct. Then we show the passwords. So we call this function. That's again transitory. And here, let's say this is transitory. So we are now in the show password list. So we are going through this part. And then we open the file. We stop if it's not if it was not possible to open a file. Then we print all the passwords. So this is all, let's say, covered by this show passwords list state. And then we free this pointer here that we allocated, and we close the file and return. So the CPU emulates the finite state machine, and as you have seen, we should only be in the sane or the transitory state. We should never go into a weird state. So how can that possibly happen? How can the CPU enter a weird state? And there are different ways how this can happen. For instance, programming mistakes or broken hardware. Maybe there are bit flips in your memory. You might have heard about the Rowhammer attack. And with the Rowhammer attack, you sometimes have bit errors in your memory without accessing it. Or maybe hardware bugs where the CPU uses the wrong value. So there was, for instance, some time ago, there was a bug in Haswell processors, and if you would run a very tight loop, they would sometimes end up with incorrect data in registers, maybe because they skipped instructions, for instance. So the program does not know that it is in a weird state, right? Also the CPU does not know that it's in a weird state now, because they are just doing their job, right? They are executing things and following the program logic, the finite state graph, based on that input. So what happens if the program now continues executing in this weird state? The transitions might still work, right? So you're now in a weird state instead of a sane state. And usually when you transition from one weird state, you also end up in another weird state. And this is what Harbaugh called the weird machine, because now you're not operating anymore on this finite state machine, but a weird machine with many weird states. And we can program the weird machine. It's a finite state machine again. So we can program this again, this weird machine, and it does something different than the original finite state machine, and that's exploitation, right? We program the weird machine. So we write programs using code, right? And this is translated into instructions that are executed by the CPU. So that means to program a device, we have to generate instructions, right? What do you think? Can we program a device without generating instructions? Well, here it says we can't. But it's wrong, right? We can also program a computer without instructions. So we need to get rid of the mindset that we require code for programming. Code is not required for programming, right? Applications accept input, and they do different things depending on the input. So if you think about it, if the application is a finite state machine, a thing that emulates a computer for a specific purpose, like this computer can sort an array, then the input actually programs the application. So this is of course an interesting perspective on this, and that's an important step for people that are working both in the red team and in the blue team. Get rid of this mindset that code is required for programming. People will just instrument the code that already exists by providing input that, well, that, what can they do? It's fine as long as the input only goes from one sane state to another sane state. But if we are jumping from weird state to weird state, then we have a problem. If the application is in a weird state, then it's programmed using input, and the attacker is controlling your computer at this point. And this is what we call pwned. If someone controls your computer, yeah. And that was an abstract definition of exploitation. Let me just go through that in a bit more detail. The exploitation process starting in a sane state of a finite state machine. The setup is we choose the right sane state, which allows us to get into a weird state if we provide the right input. And then the instantiation, we transition from one sane state to one weird state. And then the programming of the exploitation is programming the weird machine. And the goal is to break the security properties of the finite state machine. So we will program the weird machine to bypass these security checks. So with our simple password manager, how do we do that? How do we enter this weird state? How can we find the bug in the program? Can we abuse the bug in the program if there is a bug? Can we abuse it to enter a weird state? And we already get a first hint when we compile this program, and it says this one. Oh, that's interesting. The getAs function is dangerous and should not be used. Wow, okay. So maybe we should check the man page of getAs. I think you all love man pages. So let's see what it says. Yeah, and here it says getAs never use this function. It really says never use this function. Also down here it says never use getAs, because it is impossible to tell without knowing the data in advance how many characters getAs will read, and because getAs will continue to store characters past the end of the buffer. It is extremely dangerous to use. Like they say, extremely dangerous to use. You shouldn't use that function. It has been used to break computer security. Use fgetAs instead. Okay, so let's take a look at our code. So where's the bug? So here getAs is used. What's the problem here? If you have an idea, you can already write it in the chat and it will pop up here in the stream. I show the chat on the top right in the stream. Yeah, if you think about it, getAs will read, we just read it, will read as much as the user types in, and the buffer is only 16 bytes in size. So this is a bit problematic, because if the user now provides you 32 bytes, then you overflow this. You overflow the buffer. Yes, thank you. So this is absolutely correct. You overflow the buffer. So that's a problem. So let's see what happens if we run this. I will just increase, if I increase the font size more, yeah, that will be fine. We will see the chat messages then a bit larger. So if you write something in the chat, people in the stream will also see it. So let's enter a pin 1, 2, 3. Well, that's not the correct pin, so it doesn't work. Let's try something else, a longer pin. Let's see what happens. This one. Do you already have an idea what happens? Now this is way more than 16 bytes, right? So this is 1, 2, 3, 4, 5. So it's numbers, so that's really nice. So that's 10, 20, 30. So that would be 40 and probably a null byte at the end to terminate the string. So it's like 41 bytes. And what happens, and you already know that, right? You've seen those errors. It's a segmentation fault, of course. A segmentation fault. And that's interesting because a segmentation fault was not part of our finite state machine. That's not on our finite state machine, so we entered a weird state. Well, it's not very useful yet, because crashing also doesn't get us far, but maybe we can work on that a bit more. So let's check out what we can do. So this weird state was due to a programming mistake. Our finite state machine didn't have this state in it. How did we get into this weird state? So we should answer these three questions maybe. Why did we get into this weird state? What is the weird state? And third, how can we program our weird machine to do something useful instead of crashing? So let's do that. First, the why. Well, getS reads from the user until end of file, until the end of the input. Everything is stored in an array. And the array, well, all arrays have a defined size. So what if we write more data into the array? We write something else into the memory that comes right after that. Let's think about it. What was next to the variable? It's a local variable, so it is on the stack. And on the stack you will find other local variables that are adjacent to this one. In this example we didn't have any other local variables, so what else could be on the stack? And you might know that from con or from SLP or from operating systems or from maybe even other lectures that also discuss that. What is on the stack? Several pointers, like the local variables here, the base pointer and the return address. Yes, in the chat someone writes crash because the return pointer is overwritten. That's correct. That would be one possibility here. Yeah, I was not seeing the most recent messages. I think it will work like this also in this font size. Yes, the return address is overwritten. The base pointer is overwritten. Many things can go wrong here. We also have, if we are in our current function, when we call a function, right? That's what the processor does. It will save the return address on the stack. Then the function prolog will save the base pointer on the stack. Then there will be some room for local variables that's also created by the function prolog. And then we can execute our function. So let's take a look at our function and what happens here in this specific example. We have a read pin here. We put our instruction pointer on the stack, the return instruction pointer, then the base pointer. Then we use getS to read our buffer, right? And our buffer starts maybe down here and goes up here. And we entered numbers like 0, 1, 2, 3, 4, 5, and so on. So let's see what happens. Oh, this is interesting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1. Ah, interesting. So we overwrote all of this with our numbers now. That's of course a bit unfortunate. And then we print the buffer. Or actually, I think we skipped this line here. We don't print the buffer. But we return and we continue at this address that we just have overwritten. And now it's 31, 30, 39, 38. That's not a very good address. Where is that even? Somewhere. I mean, probably so the CPU will try to execute code at this address, and this is important. What happens here at this point? When we override the instruction pointer, the CPU tries to execute the code at this address. And very, very likely there is nothing mapped there at this address, and you get a page fault. And you know what happens if you get a page fault on an address. The operating system will check whether this is a meaningful address for this program, and if not, the operating system will kill the application, and this is what we call a segmentation fault. So the weird state that we have entered here is the CPU tries to execute code at an invalid address. A memory safety bug. Interesting. And one memory safety bug led to another memory safety error, accessing of an invalid address. And we just brought the CPU into this weird state by entering too many characters. So that was also quite easy. So we control now what the CPU executes by setting the instruction pointer. By providing input, we define what instruction pointer the CPU executes next. So we want to either stay in a weird state, but a useful one, or we go into a useful sane state again. For instance, we could try to get into the sane state, show the password list. Okay, let's try to do that. So we just realized that we can execute code now at arbitrary locations because we provide the pointer here. Let me just go back to this slide to show that to you again. We overrode the instruction pointer up there with a number, right? This is digits 1, 0, 9, and 8 that we provided in our input. And this is what the CPU tries to execute. So maybe we can provide a better number here, not this, not 30, 130, 39, 38. That's not a useful location. But maybe from SLP or from operating systems, you might remember this tool here, readelf. And with readelf, we can check what address this function will get in our binary, and this is the function address. So it's 08, 04, 86, and 04. So what if we provide this as a pin? Let's do that. So we have some padding here, right? So that we fill the buffer, and then null x4, null x, or x is for, this is for hex, backslash x for hex. No, 04, 86, 04, 08. Of course, because of endianness, we have to turn around this number, and then it's fine. The padding fills the buffer plus the base pointer that we have saved, and the address that we provide here overrides now the saved instruction pointer, and that's quite interesting. So let's do that. So we provide this here, echo a something, then our pointer to password manager. And let's see what happens if we do that. We run this, and we get the passwords. Very nice. We broke it. We've done it. We broke the security properties of the finite state machine. So this means that we successfully executed an exploit. Okay, let me just check the questions before I continue here. I think there were some questions on the Menti. Chat is not visible now. I think the chat is visible now. The seg fault prevents it from overriding, or it directly overrides this address. No, the seg fault doesn't do anything of that kind. The seg fault just says, well, this address doesn't make any sense, so we don't continue here. So finally, not only one new phrase per slide. Okay. I see what you mean. So the handout version of the slide. Yeah, maybe we can provide that. Okay. But we have a different setup here. I'm actually not sure whether it makes sense for operating systems, because for operating systems, you need a lot of animations around these algorithms. And if I only provide you the version that is condensed, then you don't see the animations anymore. ASLR would make this harder. Yes, that's true. ASLR would make this exploit harder. Why can we override the base pointer with an arbitrary number? Because it's not used in this example. This code didn't use the base pointer subsequently. So overwriting it. And this is also just the backed up base pointer. This is the one that we stored on the stack. If we overwrite that, it would only be used after we return to the previous function. And in this case, if the previous function doesn't use it, then it's also no problem. Okay. So what did we do? Setup, instantiation, and then we had the programming. We started in a sane state, the read pin state. The instantiation, too many characters led to the weird state. And then the programming, we programmed the weird state using the input to move to the sane state, show password list. And we have successfully developed an exploit. That's the summary of what we did. So, what more can we do? Well, we could also exploit other types of memory safety violations to overwrite data. This was a spatial memory violation, right? Because we wrote beyond the end of the buffer and we entered a weird state with that. But do we have to overwrite the saved instruction pointer? Maybe there are also other memory safety violations. So maybe we can do something more powerful, maybe a weird machine language that we can develop here. So do we have to override the instruction pointer? No, that's just one trick to get into the weird state. But in general, if we control the control flow, then we can enter weird state. So there are more ways to change the instruction pointer. There's, for instance, function pointers, there's vtables that might be stored somewhere in the program. And so overwriting the return address is not the only way to do that. So controlling this instruction pointer via this return address is not a requirement, and even controlling the instruction pointer is not a requirement. We can also go through weird states that do not control the instruction pointer. So if you control the instruction pointer, that is what we, or in general the execution, maybe not directly the instruction pointer, but more broadly the flow through the program, what the program does, instruction by instruction. That's what we call control flow hijacking. And that's a category of memory safety exploitation, control flow hijacking. And again, what is the alternative? We now got rid of the mindset that we need code to program. So if input is a way of programming a device or a program, some computer, some server, then modifying data used in a finite state machine also would allow us to do something. If we change the data to something that is not intended in the original finite state machine, then we might be able to enter a weird state. So let's assume the getS bug is fixed. Maybe it's replaced by fgetS, like this, fgetS 16. Now, no problem, right? The bug is fixed. And there's a cat. Yes. So we ignored, so far, we ignored this debug state. So what about this debug state? Yeah. I mentioned that, this is not in the original finite state machine, right? So this is one additional state that we added, and it echoes the input. But the security properties stay the same. Let's remember that statement that we had before. It should be practically infeasible for an attacker to get the password list, the output, if they don't know the input, the pin. Okay, let's see. Yes. Maybe go down here. So why does it not? My clicker does not click anymore. Now it's working again. Well, let's maybe check out compiler warnings again. And I enabled now all the warnings with W extra. All the warnings enabled. And now we still have a warning, not the get as one, but this one here. Warning, format is not a string literal and no format arguments. Wait a second, let's take a look at this code again. Printf buffer. Now, printf buffer is a security problem? Wait a second. Yes, that's a security problem, it says. So what does the man page of printf say? Printf has a man page. So let's take a look at that. The man page says code such as printf-foo often indicates a bug. Okay, so that's something we don't do. Never use printf without a format string. Often indicates a bug since foo may contain a % character, and if foo comes from untrusted user input, it may contain %n, causing the printf call to write to memory and create a security hole. Wait a second. Printf can create a security hole? Oh, no, let me ask a different question. Why can printf write to memory? That shouldn't be allowed, right? Okay. It is supposed to print text to standard output, not read something and like write something somewhere. Okay, so this is very weird. So we know how to use printf, right? And if cat wants out again, well then. Okay. This is a simple printf %d null xx %x 20 20. Okay, and then we'll print the number here. Okay. Format string parameters. What does printf do? Printf goes through this format string, parses it, and basically takes arguments from the stack. On a 32-bit machine, the arguments are on the stack. In a 64-bit machine, it's similar, but there the arguments are in registers, and only if we have too many arguments, they will be placed on the stack. So the format string parameters, %d, %s, and so on, you convert these arguments into strings and then print these strings. And one bug that you might already have experienced yourself, and it's super annoying if you run into that bug, is the number of format string parameters does not match the number of arguments. I'm sure many of you have run into that bug already. I myself had this bug very often when working in SWEP, for instance, because there for a long time we didn't have the corresponding checks. And yeah, then you print f something and it's not actually the address that you wanted to print, but it's some garbage from the stack. Okay. So the function does not know how many arguments you passed, right? Because the format string has a number of percentages in there. So how would we know that we need 2 arguments? Especially if this string comes from the user. So we fetch from registers first, then from the stack. On 64-bit machines, on 32-bit machines, it would be right from the stack. So printf with the user input now is a format string. actually. And if we provide no parameters on top of that, and if the input doesn't contain any format string, then it's fine, right? But if the user is clever enough to pass format string parameters in there, then we can output a register value or a stack value. Let's try that. So for instance, we enter this pin here, %x, %x, %x. One more. And what do we get? We get register values. Okay, or values from the stack. Okay, that's not good. That's a weird state, right? Printing values from memory is not in our finite state machine. We didn't intend that to happen. So how can we program this weird state, right? We entered a weird state again. How do we do that now? Well, %n, the little known format string parameter %n. Let's take another look at the man page there. And as you know, I love reading man pages or the POSIX standard because there's so much valuable information in there. So let's see. N, the number of characters written so far, is stored into the integer pointed to by the corresponding argument. That argument shall be an int pointer, an integer pointer, or a variant whose size matches the optionally supplied integer length modifier. Okay, so as an example, just let's take a look at this example here. Integer count, printf some string %n count, okay, and then we can print it, wrote this many characters. And this one, what will it print? Wrote 12 characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, and then %n is at 12. If there is an address on the stack, we can now write to it because we can pass %n. So the format string is on the stack, so it's an argument of printf. So we can put any value onto the stack. And that means it can be the address that we want to write to. So let's do that. So we put an address here in our string, and I will just check the questions on Menti before they are not up to date anymore. Format string exploit, exactly. Why isn't printf patched then? Oh, because people are actually using %n. You can't remove it because people are using this feature. Okay. And what do we do? So we pass this this 1, 2, 3, 4 number here just to find this later on in our prints. And then we have these values here from the stack that we want to print. And then we see enter pin. Ah, yeah, interesting. So now our value is stored on the stack. Of course, it's the buffer that's stored on the stack. Then we have %x to print our value, and we get those values out. Interesting. So what happens if we pass a different value there? Maybe this value here. Okay, interesting. Now we have a different value in there. So if we pass a pointer there, we could place a pointer on the stack, and maybe that's relevant for us. So what can we do? So here we pass maybe the address that we want to read. And %n, what does %n do? Or no, actually, maybe this is the address that we want to write to. So %n writes, let's just go back to the man page so that we make sure we got this right. So the argument shall be an integer pointer. So we want an integer pointer to be on the stack. For us, the buffer is on the stack. But if we trick this the right way, then the %n will take this integer pointer that is part of our buffer and write the number of characters written so far to this stored pointer. So what can we do there? We modify some variable and write a number to this address here. So this address, what happens here, we push this address onto the stack, right? With the buffer, we write into the buffer. Now %n will take this pointer here and write a number to it. And the number will be not 0. And if you remember this check that we had in the beginning, correct is correct, not 0. So we write now the number of characters that we wrote so far to this address here. And we get our password out again. With %n, we overwrote the correct variable at this address. So again, we didn't now overwrite the instruction pointer, but we still changed the program behavior such that we get the secret passwords out. So we programmed the weird machine using the input, and with that we transition to this sane state show password list. And there are many, many, many different memory safety violations. I've just shown 2 of them to you, but there are more memory safety violations than any one of us can fix in a lifetime, I guess. And all of these memory safety violations, they can get us into a weird state. We've only seen 2 of them. There are a lot more. Memory safety violations are a bag of tricks from which we can take one of these tricks to get into a weird state. Okay. Let's see. Well, our weird machine programs work quite simple, but actually real exploits can get super, super complicated, especially if it's about exploiting a race condition, winning a race condition to get into a weird state. Then things can get much more complicated. Or sometimes you have a sequence of operations that you have to perform, and you actually chain up things then to get a more powerful exploit. So we just jumped to a sane state of the finite state machine. But instead, we could also do something more powerful. We could inject our own code and jump to that. Or we could jump into the middle of a sane state. Injecting our own code, of course, I mean, code can also be expressed with hex characters and with \x. Then we just provide code into this buffer on the stack. And then we jump there, and then we execute the code there. Or we jump into the middle of a sane state. And this programming language for weird states or memory safety exploitation, this has developed for almost, I think soon we are getting close to 4 decades actually. Currently it's still closer to 3 decades. The Morris worm in 1988 was maybe the start, and there are different eras here. So the first was internet worm, well, internet as far as it existed back then. And this was just using a simple buffer overflow. And then we had stack buffer overflows here. We had return to libc. That was a bit later. And then this developed. So if you think about it, return to libc, we return to the same state, print the password function. Return to libc is more general, where you say, well, I return to some function in the libc, for instance. Then libc chaining, you can also chain this up and return to one libc function. And then on the stack, if you prepared the stack accordingly, you can return to the next function and the next function. And this developed into the borrowed code chunks attack in 2005, where you jump into the middle of a function. And in 2007, a newer concept was presented that was called return-oriented programming, where you specifically search for small code fragments right in front of a return so that you can just chain together a few assembly instructions and return. And with that, you can build a compiler for your programs that will compile your program into a ROP chain, return-oriented programming chain, and then execute this in some other program. And this will be Turing complete then if you have a certain number of return-oriented programming gadgets in the program. And these gadgets are some instruction like a morph operation, a push operation, maybe some arithmetic operation, and a return instruction. Blind ROP, performing these attacks without even having access to the code. Rowhammer in 2015, changing data without having access to it. Different types of memory safety problems that all help you exploiting programs, programming the weird machine. That sounds interesting. I want to learn more. Of course, that's why you are here, because you want to learn more about this. There are more techniques, very cool tricks, and yeah, we did not look at all of them. It's more important to understand the concept here, the concept of how we can exploit memory safety violations. That's why I've only shown 2 examples here. There will be more in the lecture Secure Software Development in the Masters if you are interested in that. This theory might be a bit boring, but it helps you understanding the techniques. If you want to practice that, you can participate in these Capture the Flag events, the CTF events. We have a CTF team, and that was the Los Fuzzies. And there you can try it yourself. Just get in touch with them. That's our TU Graz CTF team. Just get in touch with them. They will also help you understand these attacks and come up with more powerful attacks. And then, of course, in the SSD course, Secure Software Development in the Masters, we will also work a bit more on that. And with that, I will hide the slides for a second. And I have prepared something on the Menti. Okay. Let's see. Could you please explain once more how the overwriting of the correct variable in the case of %n works? Yes, let me just hide the Q&A for a second. So think about it. We have the buffer on the stack. Then in the buffer, I will now place an address. I will write hex characters that correspond to an address. This address is the pointer pointing to the correct variable. I just looked up the address of the correct variable, and actually that's something that you can also leak with these format string attacks with %x. You can leak the address of the correct variable. So you write the address there, and in the next step, what happens is the format string reaches this %n. And now as it reaches this %n, and if I wrote the variable to this pointer to the right offset in my string, I might have to play a bit around with the offset where it goes. Then the %n will take the number of characters printed so far and will write it to this address that was passed as an argument. Now, what we do here is we override the location where printf would expect the argument with exactly the pointer where we want printf to write to. And then to this location, it will write the number of characters, maybe 12, maybe 20, something. But in the code, if you think about the code again, it was if correct, because correct was initialized to 0 and it was set to 1 otherwise. But if I now set it to 12 or 20 or something, however many characters I wrote, then I still will go into this if and print the password list. All examples assume 32-bit systems. There are some differences between 64-bit and 32-bit systems. Explaining exploitation is much easier on 32-bit systems. We had more time to think about exploitation on 32-bit systems, but they generalize to 64-bit systems as well. On 32-bit systems, the arguments are directly passed on the stack. On 64-bit systems, they are first passed via registers. And then, of course, if you use %x, it might first print register values and not values on the stack. Yes. But if you pass enough arguments, also on 64-bit systems, the remaining arguments will be passed via the stack. So usually you would have to adapt a few things, but the exploitation is not entirely different. It's a bit more work, a bit more complicated, so more difficult to explain, but in the end, it's not much more difficult to build these exploits. What is rowhammer? Rowhammer is a problem in DRAM, and if you access DRAM in a very high frequency, let's say you have the DRAM memory of your system, have that here, and you access two locations in a very high frequency, then memory in another location, none of these two, but maybe in proximity to those two, would change. The bit value would change, and then it's a wrong value in there. Okay. Let's see. We have some more things on Menti. Is rowhammer obsolete with DDR5? If you ask me, I mean, I haven't worked with DDR5 yet, but I would bet that it's not obsolete. Rowhammer won't vanish anytime soon. Let me just ask you a question right now. For the system security lectures, we could take a break now. 15-minute break. No break. We can change the lecture start to 10 if you want to, or we can go from 9:30 to 11:30 if you want to without any break. But we can also take a break, 15 minutes. And it looks like the majority wants to have a break. If you don't want to have a break, just vote now. Yeah, it's still a clear majority here. And there's a question in the Q&A whether I invented rowhammer. No, I have done a lot of research on rowhammer, but I did not invent rowhammer. Okay. So it looks like most of you, actually now it's 50 to 40. So if you really want to skip the break, you have to vote. I'll give you a few more seconds to vote. I think it's clear. Most of you want to have a break, and that means we also take the break now. I would not make it 15 minutes today because we still have a lot of slides to cover. So I would only make it a break until 11. So that means it's like 7 minutes of break. See you then after the break. Welcome back. So we continue with the lecture, and yeah. Now we already had the break, so we can skip this one. Oh, I have a word. I'm not sure what the word cloud will be used for, so I have to check. I think I prepared something on one slide, and there we can use it then. But I'm a bit confused by the title word cloud here. Let's just continue for now with the presentation. As you can see, finding these flaws also gives us a good motivation to fix them. We got rid of the getAs function. We got rid of the format string vulnerability, and now we couldn't find any other bugs. So looks like our code is secure. Looks secure. Can we show that our code is not exploitable? Can we prove that in some sense? Difficult. Not really, right? We would need to check all weird states whether they are exploitable, but how do we know which weird states are reachable? And there are many weird states. And it also depends on the attacker model. What can the attacker actually do? It's difficult to think about attacker models that have not yet been discovered. So it is necessary to research attacks to come up with the defenses that we need. Okay. Let's take a step back and go more up to a higher level of this topic. Exploitation. Who is interested in exploitation in general? And maybe this is a good point. Maybe this is an idea. We can use the word cloud here. So the question is, who is interested in exploitation? Just write your ideas here. Who could be interested in exploitation? Well, of course. But maybe also you? Of course. Eve, okay, Eve is interested in exploitation. Hackers. Secret Service, that's interesting. Zerodium, yes, Zerodium might be interested in that. White Hat, Black Hat hackers. Then we have ransom. Oh, yeah, companies or individuals that produce ransomware. Sure, that's an easy way to monetize your vulnerability search. Yeah. Okay, so it sounds like you have an idea of who could be interested in that. Let's just continue, and we will continue with what I have added on the slides here. Who is interested in exploitation? Criminals, because they want to exploit them and make money of that. Vendors, because they want to patch it. And governments, because they want to protect you. I mean, that makes sense, right? So, 0 days. Maybe you are also interested in exploitation in 0 days, in jailbreaks. Get root access on your devices that you bought, but don't have all the permissions on these devices that you would like to have. For instance, for iOS, there have been many jailbreaks for iOS, very often in the content of actual exploitation that the users don't want. But think about, for instance, the Wii, the gaming console. There was a buffer overflow in the game The Legend of Zelda Twilight Princess, and for some time it was difficult to get the game because the demand was so high, because people were just buying it because of the buffer overflow, because it allowed to root the Wii. And if you do that, then of course you have more capabilities. You can bypass copyright protections, for instance. and it gives you more control over your own device here. So they bought the game to exploit the buffer overflow and then jailbreak the V. In the PlayStation 2, there was a buffer overflow in the BIOS. In the PlayStation 3, there was a heap overflow. In the Xbox, there were buffer overflows in save games. Also an interesting thing, save games. You have some state, you save it into a file, right? And how do you do that? I don't know. Maybe you have a struct, a packed struct. You write this into a file, and maybe there are buffers in there or pointers in there. And if you write it out to the file and read it back, nothing will go wrong. But what if someone modifies the file and then it doesn't match anymore? Buffer overflows in save games. And of course, we also had that in the word cloud already. Zerodium is a company that pays bug bounties. They buy your exploit and then they will sell that to someone else. And they give you a lot of money, like what does it say here, up to $1.5 million. And I think this is not the most recent plot, not most recent table of what they pay. I think by now the numbers went even higher. So if you have a high severity bug in a product that they are very much interested in, then this is a lot of money. Should you do that? Should you pay? Should you sell your exploits to them? You have to think about what they will do with that, right? What are they going to do with this exploit? And if this is ethically fine with you. These exploits, for instance, you might know that governments have an interest in computer and network surveillance, right? There are some state-sponsored Trojan horses. For instance, in Germany, there was the Bundestrojaner. In Switzerland, they called it the Mini-Panzer and Megapanzer, also Trojan horses. And in Austria, we also have something, the Sicherheitspaket. There were also the NSA exploits, the Shadow Broker Leak. And for the smaller countries, maybe even for Germany, but less so maybe about the NSA. So the NSA had several exploits in there that no one knew before, and they existed in this Shadow Broker Leak, this leak. They were in there for several years. Exploits for bugs that were not patched. Everyone was still running software with these bugs. And once this was released, we also know what happened. There were ransomware softwares that exploited these bugs. So everyone is at risk if bugs are not fixed. But on the other side, governments believe that they need to keep these vulnerabilities in the software that you use to keep you safe. And yes, this might be different perspectives, but in the end, the statement is that they need to keep you insecure, your systems insecure, to keep you safe. How do they do that? How do these Trojan horses work? So the NSA has enough resources to search for vulnerabilities themselves, but possibly they also buy exploits from companies like Zerodium, or maybe even on the black market. Then Germany, for instance, much fewer resources, so there it's less clear how they approach that. But for Austria and Switzerland, would they realistically go and set up their own departments that search for bugs in popular software and then keep that secret to make sure that their Trojan horses keep working? Because think about it, the Trojan horse is a software that only can operate on your system if they have an unpatched vulnerability in there. Otherwise, they won't work. So they need that unpatched vulnerability. And what happens here, for Austria, for instance, they need to buy these 0 days somewhere. They need to buy these unpatched vulnerabilities somewhere. And if Zerodium buys them from you for 1.5 millions, you can imagine that they will not sell it for exactly the same price. So we will pay millions and millions for exploits, for unpatched bugs. And instead of patching them, we will make sure that they are not patched to keep everyone safe. Let's talk a bit more about the blue team. We talked so much about the red team. Let's talk about the blue team, the defenders. That's maybe a bit more positive. Regarding Xbox save games, isn't saving memory pointers to a file generally a bad idea? Yes, if you save pointers into a file, that's a bad idea. But also if you would have a buffer, if you would save a buffer into a file, how would you save the buffer if it has a variable length? Would it be null terminated? Would it be a buffer plus the number of bytes of the buffer? What if the user is malicious and changes the number of bytes so that it doesn't fit to this buffer anymore? Then maybe weird things are loaded into memory. What is the Sicherheitspaket in detail? I think you can read up on that on the internet somewhere, but it included that the state will use some mechanism to read messages that are end-to-end encrypted. And if something is end-to-end encrypted, you can only attack either of the ends. And if both ends are a mobile device, then you need some software on that mobile device to read the message. Why is it called 0 days? Because the vendor, well, a 0 day, once a bug becomes known to the public, or before it is known to the public or to the vendor, that's what you call a 0 day. So a bug that is not known to the vendor, not known to the public. If it's known to the public, then it's also known to the vendor. If it's known to the vendor has some time to patch it, right? So that would be the time where you stop either when disclosing it to the vendor or when disclosing it to the public. That's where things might stop being called a 0 day. In general, it's an expression for unpatched vulnerability, because there were 0 days of time to patch it. There was no time to patch it. Okay, so let's continue. Defending against attacks is surprisingly hard. In classical war games, there is a 3-to-1 rule. The attacker needs at least 3 times as many soldiers as the defender. That's not a law, but a rule of the thumb. So in computer science, things are much worse. In computer science, the defender has a disadvantage. The attacker only needs to find one vulnerability, and that bypasses all the defenses. The defender, on the other side, has to defend against all possible attacks. And that means the defender has no chance, right? If the defender misses one vulnerability, the attacker wins. And thinking about memory safety violations, because some people mentioned, well, memory safety violations, we wouldn't have them with Rust. Yes, we also wouldn't have them with many other languages, like Java, for instance. As soon as they interface with lower level things, you still have them. And also there are enough other types of vulnerabilities that you can still have. Also from classical war games, the best defense is a good offense. Well, no, it doesn't work. So what do we do? There are mainly 2 strategies. The strategy 1 is red team finds all the bugs and reports them to the blue team, and the blue team fixes them. Or strategy 2, the blue team tries to find generic mechanism, and the red team should then not be able to exploit the program anymore. Okay. Very often strategy 1 is used because it seems simple and cheap. If a bug is discovered, you fix it, you're done. And if you think about it, you can even reason about how difficult it is to exploit a program. It took an attacker or researcher more than n months to find a bug, so the cost of finding the next bug is greater or equal to n months, right? No, that's completely wrong, of course, because I might find more bugs, or if more people start looking, they might find more bugs. For instance, think about the early 2020. Zoom was a product that was already in the IT security news in I think it was 2018, maybe also 2019, because they screwed up their security. And it took several months until there was once more a security screw up by Zoom. And then in early 2020, when everyone started using Zoom, also security researchers started looking at that and checked, well, is Zoom actually secure? They had some problems in the past. Did they patch all of that? And then they started looking, and then suddenly new bugs and security problems in Zoom were discovered on a daily basis. So you can't say, well, oh, before it was only one bug every 6 months. Suddenly, everyone saw that the security of Zoom was much more devastating than they thought. And it was basically, not only compromising your communication, which was readable to basically everyone on the internet that could read your network packets. It was a lot worse. It was compromising the security of your systems. In some cases, it was itself using techniques that we would use to write exploits to install something on the system. And if the attacker gets control over Zoom, they also gain that ability and could then escalate to kernel privileges or root privileges because Zoom is installed. And that's of course a problem if you install software on a system and then this software undermines the entire security of your system. So just a quick recap. We defined exploitation as a three-step procedure: setup, instantiation, and then programming. So we choose the sane state, which allows getting into weird state. Then we transition from the sane state into weird state, and then we program the weird machine. The fix prevents just one weird machine, or its program, the programming of the weird machine. If there are similar bugs, then you will have similar weird machines, okay? But if an attacker found one bug, there might be other similar bugs, and it will be a lot easier to find and exploit similar bugs in your program now. Let's assume you have in your program there are 17 different buffers, and then they realized, oh, one of them can be overflowed, and it took them months to find this bug. They will probably only need a few days or maybe even a few hours to find the similar bug in another buffer. And of course, then you can search for more bugs, but this only works until there are no similar bugs left anymore. If you would plot this, basically the expectation would be that with an increasing number of bugs, the cost also grows linearly. So it's always the same cost to find a new bug. But the reality is more like this. In the beginning, you have to understand the program, how it works. And then as soon as you've done this initial work, then it's fairly easy to find new bugs. And that's true for simple bugs, for complex bugs. You always have to invest some more time to come up with an exploit for that complex bug. For simple bugs, it looks even different, right? Because there, less investment in the beginning, and then a very long valley where it's super cheap to get one more bug. And then simple bugs become scarce, and then it becomes a lot more work to find one more simple bug in the program. So what we do in our research as a university, we try to come up with a more generic way to that, right? So we want to remove or eliminate entire classes of bugs. For instance, the class of buffer overflows, by coming up with a defense that makes buffer overflows impossible. And this can be extremely hard. So that's why it's also not easy to find bug-free programs, but we already win if we prevent exploitation, right? Because then you might be able to crash the program, but you cannot exploit it anymore. And we have a solid definition of exploitation. So which step of exploitation can we prevent? We cannot prevent the setup step because every transition here is sane and the state is defined. We can try to prevent instantiation and programming. That's what we can do. So we start with instantiation. Let's take a look at that. We again use our simple password manager as an example. And here I have again the finite state machine, read pin, show pin. Well, if it's in this debug state, if it's correct, show the password list, and then the error message here. And we don't exploit the getters and the printf now, just going through this example. So we assume the bugs are still in there, and we assume the red team did not find the bugs yet. So we don't know about the getters and the printf bug in there. So what does the blue team do now if it wants to defend against these attacks that it doesn't know of? The blue team has to know roughly about possible attacks. Protecting against a yet unknown attack is often not possible, or it comes with great costs, performance overheads, because you have to do too many checks, because you don't know whether they will be necessary. So let's assume we already know about stack buffer overflows, and we want to prevent this instantiation step. So what can we do to prevent that an attacker can get into a weird state using a buffer overflow? We want the program to rather die than being attacker controlled. So with this stack overflow, we override the saved return address. Can we stop that from happening? Can we stop the program from overwriting, or the stack overflow from overwriting the saved return address? Maybe a question for the chat here. Can we make it read-only, the return address? We cannot. We cannot make it read-only because we have write permissions only on a page level granularity. So it has to be writable. But here's a simple idea. We put a known random value between the buffer and the saved return address. A known random value. And we call this a canary. Exactly like this bird. The canary will be overwritten first before we overwrite the return address, because it's right in the middle between the buffer and the return address. And before we return from a function, we check whether the canary has the correct value. And if not, then it's a buffer overflow and we kill the program. And canaries, historically, the word canary, well, it's a bird. Where does this use of a canary for safety come from? For memory safety and for safety in general? It's from coal mine workers that brought canaries into the coal mine. And when they were down there and suddenly there was some gas coming from somewhere where people would suffocate, then the canary would be in its cage on the bottom of the on the ground, and the canary would die first. So if the canary stops making a sound, that would be the point where you have to run. For our program with canaries, it's similar. Now we place the canary here on the stack. It's a random number and it's between the instruction pointer and the base pointer and the buffer. And now if we use getS, we overwrite this canary as well. And that's very nice. Before return, we check the canary. It's not the same. We exit the program. Great. Stack canaries are enabled by default in GCC, but only for buffers that are larger than 8 bytes. And you can use -f stack protector -all to protect all buffers. Let's see whether this works for us. So we run this, and what happens if we run this? We see that the program now prints an error. Stack smashing detected, password manager terminated. Right, we fixed the class of Stack Overflow bugs. That's great. So we fixed an entire class of bugs. And that in a language that is not memory safe, in C. So we don't have to switch to Rust to make things memory safe. We could also do that in C. So this is great. The canary protects every stack buffer from being used to get into a weird state, right? No, wrong. That's not how it works. Okay, let's take a step back. So maybe we only fixed simple buffer overflows. Simple buffer overflows on the stack cannot get into an exploitable weird state, but think about it. We had this format string attack, and there we used %x. What would you read with %x? Let me just refresh this window because I didn't see any responses anymore. Ah, yeah, good thing we don't have to kill birds for system security's sake. Yeah, it's just virtual birds. So it's fine then, because they are not real. Okay. With the printf bug, with %x, if I pass %x as user input there, I can read data from the stack. And that means I can leak the canary using the printf bug or an out-of-bounds read on a buffer. So that means we only prevented part of a class of bugs. So still not really that nice. There are still other ways to get into a weird state. And we want something more generic, even if it's less powerful. Academics are also are always looking for these generic mitigation steps. So what is the alternative to preventing the instantiation step here? We can take a look at the other steps. So overwriting the saved instruction pointer on the stack gets us into a weird state. So maybe we can have separate locations for addresses and buffers. A very simple idea. We use two different stacks, one safe stack for just addresses and an unsafe stack just for buffers. Why not? So simple variables and return values would be on the safe stack and buffers on the unsafe stack. Very nice. Now buffer overflows cannot overwrite the return address anymore. So let's take a look at this example. Normal stack frame would be like this. Local variables here, base pointer here, return address here. In the other case with the unsafe and the safe stack, we have the return address and the base pointer here and local variables down here. And we call now into a function. This is the last frame, and so the return address is pushed onto the stack, safe stack, normal stack, and the base pointer is pushed on the stack here and here. Local variables here, and in the other example here. So you can see it's really split up now. You can use that. CLang supports safe stacks with a compile flag. It's not implemented in GCC yet, but actually maybe by now it is. Let's try whether the bug is still exploitable with SafeStack. So we use the flag fsanitize SafeStack, and with that we can now provide our pin again with 40 something characters. And what happens? Nothing. Interesting. Now it says just wrong pin, nothing bad happened. Yeah, sounds good. But until now we only prevented a small class of bugs, and this looks a bit like a cat and mouse game, right? We find some small class of bugs, we prevent it, and then someone comes up with a newer attack, and then we come up with a defense against that. But we will never be finished with that, right? So this works, it adds protection, but we have to combine a lot of countermeasures if we want to continue that way. And every countermeasure costs, right? Because here we place more things on the stack, or maybe we even need a second stack for every thread. So this costs performance, memory. We want something more generic. Maybe even if it's not as powerful as specific countermeasures. So something that was already mentioned on Menti before was ASLR, Address Space Layout Randomization. Randomness is often used in security. It's a probabilistic approach. And the assumption here is that the attacker can jump to any memory location, right? By overwriting the return address, for instance. But what if the memory locations are all unpredictable? Then the attacker cannot just jump to some location because the location is not known anymore. So if you take a look at the memory layout that you might know from operating systems or from SLT with code data and everything here, then what ASLR does is it randomizes the position of the program part. So they would be at different offsets. Every time you run the program, different offset. And that means the attacker cannot predict where the location of a function is and cannot jump to a sane or injected state. This is powerful on 64-bit systems because on 64-bit systems the user space has 128 terabytes of size, and that means it's very difficult to predict where exactly your function will be. And this will even increase, so the next generation is already there with 64 petabytes of address space for the user. ASLR, Address Space Layout Randomization, is not only useful for buffer overflows. It's useful for a broad range of attacks that try to inject addresses somewhere. Every attack where you inject an address somewhere is affected by ASLR. The disadvantage is it's only probabilistic. And we have two assumptions here. There are no leaks of addresses, because if you leak an address, you have broken ASLR immediately. And the randomization is large enough. Brute force shouldn't be able to break ASLR. On 64-bit systems, that's fine, right? On 64-bit systems, ASLR can make exploitation really, really hard. On 32-bit systems, not so much. The advantage of ASLR is it costs nearly nothing, because it doesn't make a difference whether your memory is mapped here or there. It doesn't make any difference. So it costs nearly nothing. ASLR is super cheap, but nevertheless very effective, and it's very widely used. Linux uses it since 2005, since 2014 in the kernel, and Linux distributions are also applying it to more and more software as we continue down the years. Windows uses it since 2007, Android and iOS since 2011, macOS since 2011, since 2012 in the kernel. And ASLR prevented many single bug exploits, as they now fail with a very high probability. Now, let's assume the attacker still found a way to get into a weird state. Maybe we can come up with some method to prevent the programming step. So that would be the last resort here to prevent the exploitation. They are already in, we just want to stop them from programming our weird machine. So the attacker uses the input stream to program the weird machine. If they do that, I mean, we could filter the input stream, right? We could say, oh, these characters are not allowed. But that's not always possible and also not very generic. But it's something that you should do in many contexts. So if you get user input, restrict it to the characters that you are fine with handling and don't allow any other characters that you haven't thought of. Or make the finite state machine aware of itself. The finite state machine should know which states and transitions are allowed, and you want to prevent all transitions that are not in the original finite state machine. That means every state has to check whether the target is an indirect jump, is a correct address according to the finite state machine, whether the saved return address points to a previous state, so whether you would be going back to a previous state. And the finite state machine will force the program to stay on this graph. So let's take a look at this. So we have all the transitions here. Read pin. Can I go from read pin to error message? No, it's not allowed. Can I go from read pin to show password list? No, also not allowed. The only transition from read pin that is allowed is show pin. From show pin, can I go to error message? No. To show password list? No. Can I go to read pin? Yeah, I mean, it's coming from there, so maybe that's allowed, yeah. Show pin. We can go forward to correct. Can this one go back? Yeah, there maybe it can. From correct, can we go to show password list? Yes. Can we go to error message? Yes, also in the other case. And then here from show password list, we can go back to the correct state, but also, I mean, then we can also go back or terminate the program. From error message, we actually go back to read pin, so that's the only transition that is allowed from here. Or back to the correct check, because it's a backlink. Okay. Control flow integrity sounds very simple, but it's actually difficult to implement. Someone in the Menti mentions we could read the canary. Yes, with the printf format string attack, for instance, you can leak a canary. And you can also leak ASLR addresses and by that break ASLR. Are there still this many 32-bit systems out there? Isn't 64-bit state of the art? Absolutely, but there are still 32-bit systems out there. Would ASLR still work the same if the binary would be compiled statically? I think you could in principle do that. Most compilers don't do that today. So if you compile with a static flag, if you compile the binary statically, then it would disable ASLR because it makes the work for the compiler easier. Okay. But I wouldn't say that it's in principle impossible. It's just more work that the compiler and maybe also the operating system loader would have to do. Control flow integrity, as I said, sounds simple, but it's difficult. The control flow graph must be correctly constructed, and that's not easy. Function pointers can also not be protected unless you have a very limited set of target destinations where you can jump. Some functions might have many call locations and therefore return locations. And that's again a problem because then you can return to them, right? Through this backlink. Still, there are usable implementations in CLang from Microsoft. I think I'm not sure whether GCC by now also added that, but a few years ago it was just CLang and Microsoft. Exploitation is still possible here, right? The integrity checks are usually very coarse-grained, so that means that you can jump into another function maybe with some offset, but not with any offset, or you can jump always to a start of a function, but not into a function. So very coarse-grained checks. Let's take a look at this example here. We have our main function. We have commands help, unlock, and quit. Function debug. We parse a command. So if the argument counter is greater than 1, then we just take the argument a to I. So we make this a number, help, unlock, quit, debug, and then we call this command. Otherwise we say, oh, usage, you're using this wrong. And this is password manager UI with 0 to 2 as a command. Okay. What else do we have if we call the debug function? Then we actually start a shell with system.bin bash. Okay. For debugging, users shouldn't do that, right? We have 0, 1, 2, 3 would not be allowed as an input, or would it? So we have the function, we have a function pointer here, we have a function help, display help message, unlock password manager, quit, prints by, and then exits. So we store our functions right here in this function pointer array. Help, this function pointer, unlock, this function pointer, quit, and debug. And usage is called directly. Okay, and then we just use one of these function pointers. Sure. So why can't we use this debugging function here? Because this one goes to the commands array, not the debugging array. So this is why we cannot call this debug function here with user input. Let's see what happens. We compile this with CLang, we run this, we are not using it correctly. 0 works, 1 works. Okay, yeah, we cancel this with Control C. Then 2, okay, just prints by. Okay, let's pass some other value, 10. Segmentation fault. Oh, okay, so segmentation fault, that again doesn't sound very good, right? But let's check what it says. Password manager user UI -1. Like, oh, wait. How? That should not be possible, right? Okay. So why if we pass -1 it works? So let's check why that works. So -1, if you take a look at this array, if you go beyond it, it's out of bounds. But if you go below, it's actually in another array. So the checks are very, very coarse-grained. Let's pass more flags here. fsanitize minus fsanitize CFI, flto, visibility, and now we should get a better control flow integrity check here. The previous one was just the buffer overflow case that we already knew, right? We overwrote the return address and it crashed. Okay. Or actually, no, in this example, we were actually trying to execute probably the base pointer, or maybe, let me just go back to the code so that we really say this correctly. So the next element after this one would be the last argument that is on the stack in a 32-bit system. In a 64-bit system, the next element on the stack would be the base pointer here. So we would try to execute the base pointer as a function. In this example, if it's a 32-bit, then we would try to execute the argument pointer. And this was not clear whether it's 64 or 32 bits, but either way, we would not be executing anything useful. So it crashes, it will be exploitable. Let's see whether CFI, control flow integrity, fixes that. So we pass the flags for that. 0, okay, works similar as before. Let's pass 10. Runtime error, control flow integrity check for type void. It's a function. Failed during indirect function call. Yes. Okay, doesn't work. Let's try -1. Also doesn't work. So as you can see, control flow integrity is one way to prevent exploitation in the programming step. So we discussed techniques to prevent exploitation in the instantiation step, canaries and ASLR. And for control flow integrity, that would prevent the programming step. But there are more techniques that you can look up. And these are already a good start to provide good protection. But again, they can be circumvented. No countermeasure is really absolute. But why do we use countermeasures then if they can be circumvented? We raise the bar. Usually the argument is we have to increase the cost, raise the bar for an attacker. Or many layers of security make it a lot harder for an attacker. You will find expressions like defense in depth. If the company knows, okay, this could become a problem at some point, let's apply a defense in depth here. If someone gets this far, then they will still be stopped by this countermeasure. So this is partly true, but however, it costs something. And usually there's a trade-off. If you increase the costs for the attacker, usually also you have increased costs for the users in terms of slower programs, more memory consumption, or even usability problems that come with the raised bar. So the user has to pay the costs all the time. The attacker only has to pay the cost once. So that's a problem. Now the defender should decide whether such a trade-off is worth for individual cases. The presented countermeasures, they have a good trade-off between cost and security, especially ASLR, because it's basically for free. And that's the reason why they are widely used. Future hardware might even implement countermeasures in hardware to reduce the costs further. But what can we do in the meantime? What if we cannot stop an attacker? Maybe we are not able to stop this, but maybe we can restrict the attacker after the exploit. And that's the last topic that I want to start today. I might be able to cover all the slides. Otherwise, we will continue with the rest of the slides in the next lecture, but I will try to finish at 12. When we cannot stop the attacker, we can still restrict the attacker after the exploit. We can protect our system even if the application is completely compromised, like Zoom. If you run Zoom and Zoom is completely compromised by the attacker, you can run Zoom in a sandbox, of course. Make sure that it can't destroy anything. And sandboxing, for instance, with Docker can be very easy, just one command. And Docker is one example. Actually, Docker is not even the easiest one. FireJail, for instance, is much easier to run. There you can just put it in one line and it starts. You don't have to set up anything here. This one, yeah, if you know the flags, then maybe. And here again, I enter some weird pin, and maybe I now have code execution in this Docker container. But in this Docker container, I can't do anything. It's a read-only file system. I can't do anything. No network, nothing. So an attacker cannot do much there. File system is read-only. No files can be changed or created. No files of the host computer are visible except the program and the password list. Of course, this would be compromised. But where do you send the data? There's no network connection. So it's not easy to exfiltrate the data from there. And then it gets a lot more complicated. And that's maybe the research area that my group is interested in. How can you still exfiltrate data in such scenarios? So even if a program is now compromised by the attacker cannot harm the rest of the system. And that's great. What do we need to do as defenders? We always need to expect the worst case. The worst case could happen. In this case, the attacker found an exploitable bug, circumvented all countermeasures, got a shell in the sandbox, and was able to read the password file. That's no problem if the file is encrypted and the key is derived from the correct pin. Assuming that the crypto is good and you correctly used it, that should be fine. That's where we use cryptography, right? If that's not the case, then the attacker got the password list. But if we encrypt the data, do we even benefit from a sandbox? Then the attacker cannot steal anything anyway, right? Wrong, of course, wrong. Without the sandbox, the attacker can create or modify files. The attacker could install a keylogger or other malicious software, or replace the password manager with a manipulated one, leaking the PIN. So if you're saying like, oh, I want to run Zoom, but I don't want to run it in a sandbox because that's inconvenient. And you know that Zoom has been full of vulnerabilities that could compromise your systems. It's not about that someone could attack your Zoom client and spy on you while you are having video calls. It's about protecting the rest of your system to make sure that compromising Zoom doesn't mean that all the other things on your computer are also compromised. Even the best crypto does not help if the system is compromised. So the best practice here is we never assume perfect countermeasures or bug-free code. You encrypt the data in case it leaks. It will leak at some point. You minimize the privileges, for instance, by using sandboxes, by using unprivileged users. The server should not run as root, for instance. You log everything. That's also a very important part. You log everything. In case of an attack, you have the chance to find and sue the attacker. This is actually a large part why our world works, not because attacks are impossible, but if you mount them, you are sued and you go to prison. That's a big part of why not a lot more things are broken. A compiler can help to harden your application. For instance, with CompileFlex, I've shown you a few today. There's one more that I want to mention here, for instance, dFortify Source. You can check out on the internet what this one does. It's a good idea to use this when you want to build secure applications. So what takeaways do we have? Never ignore compiler warnings. Those were just warnings, right? And we transformed them into end-to-end exploits that give us not only the password list, but in the end, even code execution on the system. Never disable the countermeasures. The default countermeasures are useful. Don't disable them. Enable countermeasures that are cheap, like ASLR. And consider enabling stronger countermeasures such as CFI. And if you have an application, always consider sandboxing. If you sandbox it, you limit the damage that an attacker can do. Defending software is hard, but it's not impossible, right? We can make it harder and harder for the attackers. We might not reach a point where software is perfectly unattackable, unexploitable, but we will get to a point where it's not reasonable for an attacker anymore to invest that much energy. Defenses are important to raise the costs for an attacker, and the problem is that the costs for the attacker always go lower, because the first time you mount an attack, it's super complicated and super expensive. And then the next time you mount this, you will write a script that automates parts, and it's already a lot cheaper. So attacks only get cheaper and attacks only get better. And that means security is a cat and mouse game full of repetitions, and it won't change. This will not change. We will have that in the same way in the future. The best countermeasure is don't have bugs, but of course we know that yeah, maybe impossible, but we can try to minimize the number of bugs. A realistic view is, yeah, impossible to have bug-free code, but we minimize the number of bugs. And with that, we are at the end of the lecture, and I'm actually on time. That's interesting. So I can open the Q&A. So quick fix for warnings. Also add W errors, so you have no warnings anymore. Oh yes, that's a good one. We did that in operating systems, I think, in SWEP by default, and people didn't like it. So, is a VM a type of sandbox? Yeah, I would say a VM is a particularly strong type of sandbox, yeah. You can use a VM for sandboxing. Since when is there a function keyword in C? There is not. There is no function keyword in C. I used a typedef to typedef a function pointer. And this typedef was called function. Is Zoom now safe to use? I wouldn't say, I wouldn't make any statements about that. Okay. If a system is not open source, how do you start an attack? Just try out 1,000 things and invest weeks? Think about the example that we just had today, the pin entry example. You see, when you start with that, you see that there is a crash. You see that it crashes on an address, and then you just play around with the input and see whether the crash changes, for instance, the address that was accessed. In one case, we were able to see that it crashed on the address that we provided. And that means we already have found a direct way to provide a function pointer. And then if you don't have the source code of the application, well, the ELF binary still has functions in there, and you can look at the object code and check where functions start. There are disassembly tools, there are reverse engineering tools that help you with that can take a binary and reconstruct to some extent functions and even interactions with between these functions. So they might not have valuable names then, but then you can give them names, and then suddenly the program starts making more and more sense. And this is usually how you would approach that if it's not open source. What is sandboxing? For instance, Docker. Docker is a sandbox, but also FireJail is a sandbox. And the idea of sandboxing is you run a program in a sandbox, and in a sandbox, well, that's not the real system. So you don't see the real system. The attacker doesn't see the real system, cannot interact with the real system. If you're interested in that, we will actually write our own sandbox in secure software development. That's part of the lecture there we have it on the slides. We write a sandbox from scratch. Will we go over fuzzing? I don't think we cover fuzzing in this lecture, but in secure software development we talk about fuzzing. Then we have any hints for assignment P2? Do we have to know how to use a GDB? I'm not very much involved with the practicals, so this is something that you better ask on the Discord channel or in the practicals units. But I would expect that GDB usage, I mean, that was already required in SLP. So I would expect that they use it also. Should web servers also run in a sandbox too then? Yes, if possible, yes. Why wouldn't you run something in a sandbox if you can? Do you run all your applications in a sandbox? I run some applications in a sandbox, and Some applications I don't run in a sandbox because it would be too inconvenient. And that's the problem. The user has to pay the cost. If it's super inconvenient to do that, then people don't do that. I didn't use GDB in SLT once. Wasn't necessary. Yeah, missed opportunity. You could have. Cubes OS, your choice of OS, then no. Of course, I use SWEP and nothing else. Okay, let's see. No more questions. Let's finish the lecture here. We are on time. Thank you for being here and see you next week.